So in a moment, I'm going to hand over to Kim Warren, who's going to deliver a workshop, online workshop on getting started with system dynamics. So Kim is a highly experienced strategy professional, teacher and writer. He spent 15 years in senior strategy roles before joining the London Business School to teach on MBA and executive programs. And over this period, he came to the dawning realization that the strategic frameworks weren't really as fit for purpose as they may be. And so he took his thinking, applied system dynamics thinking along with that, and created the strategy dynamics approach, which he has applied in numerous sectors, including the third sector, and has made some real cutting edge and impactful projects over the years. In addition to that, he's a prize winning author in the field of system dynamics and won the Forrester Award in 2005, one of the most prestigious system dynamics awards there is. And finally, he has developed Systea, a specific system dynamics tool to support his consultancy approach and also to support teaching and training in system dynamics. And so I am delighted to be able to hand over to Kim Warren to deliver his workshop. I hope you will enjoy the day. Thank you very much.
Fabulous. Thank you for that introduction, Sean, and welcome everybody to today's event. My bit of this day is to deliver this short tutorial to introduce people to what system dynamics is and how it works and what you can do with it. You won't be an expert at the end of 2.5 hours, but hopefully you'll have a reasonable idea how these models get built and enough to give you some ideas about modeling that you might want to do. It would be very helpful for me actually to have an idea of the audience that we've got here. So I believe that the organisers have a way of asking you to vote on things. And the first thing I'd like you to vote on is your level of experience. So there are 3 possible answers to this. Answer number 1 is you're quite experienced. You've actually built quite some number of models before. The second possible answer is you're quite new. You've built a model or 2, but you're still kind of feeling your way with system dynamics. And answer number 3 is you're totally new and haven't got a clue. So perhaps if you could just answer that question there. I don't know how you do that or how the organisers tell me what the answer is, but I guess I'll find that out very shortly.
Kim, this is Diego. I launched the poll, and and right now they're answering. I don't know if you see the votes right now, but we have at the moment around 40% are quite new, 25% are totally new, and the other 40% is moderate to highly experienced.
Okay, fabulous. That's really good. Thank you very much. And the second question is, how many of you are students? How many of you are other academics? And I'd put PhDs in with other academics rather than, no, I wouldn't. PhDs count yourself as students as well. Answer number 2 is whether you are otherwise an academic, and answer number 3 is are you in professional practice? And you can answer yes to more than one of those if you want.
Okay, so I launched that poll, and around 50% are other academics, and the other 40% are pro practitioners, and just 10% are students.
Oh, wow. It's surprising. Oh, good. Okay. Right. Let's crack on with what we're going to do. So what you can see on screen is what we were going to do today, but we're not. For obvious reasons. How do I get my presentation to move on to the next slide. There. For obvious reasons, we have switched our attention this morning, and we're going to show you how to make a start on modelling by actually trying to model epidemics and countermeasures. At this point, I should perhaps introduce Maurice Glickman, who I hope is a co-presenter on this. I hope he's also unmuted. Maurice is a long time friend and collaborator. Was formerly a partner at McKinsey in their business dynamics practice, and it's his fault that I got started on this project on modelling epidemics, and we'll tell you a bit more about that in a moment. Maurice, do you want to say hello?
Hi, I don't know if you can hear me. Can you hear me?
Yep, certainly can.
Oh, okay, thank you, Kim. I seem to be the person whose fault it is for a lot of things, but I'm glad it's this one. So thanks for that. And it's been an enormous pleasure to work with you over the past couple of weeks to get what we're doing started. And I hope by the end of the session, which I teasingly said, let's try and hijack it. We may get some more collaborators involved in the initiative we're working on. So I'll just let you run with it, Kim. Please let me know if I can answer any questions along the way, and otherwise I'll stay quiet.
Okay. Yeah, thanks a lot. I should say, by the way, that there are other even more experienced people than me in this field, both in the UK and internationally in the system dynamics field, who are doing projects every bit as powerful and useful on COVID-19 as what we're going to show you. So I don't want for a moment to imply that we're doing anything that other people are not just as good at doing. So you're going to actually start on this, and I'm going to demonstrate a simple system dynamics model, and you're going to build that model with me. And we will show you how to share that model with other people, and we will share our model with you. And then I'm just going to backtrack a bit and specify the approach that we take to building system dynamics models. So I call it Agile SD because it has some similarities with the process that has been followed for some decades now in the IT field for building IT systems with people very quickly. And if we have time, I'll try to point to some other useful resources. So first of all, what is system dynamics? It's the use of quantified simulation models to understand and manage issues that feature complex behavior arising from something called stock accumulation. That will become clear what that is at some point. And from feedback. And that there is a related field that might be called feedback systems thinking, and that is a qualitative approach to building causal maps of how things, how a group of stakeholders in an issue feel that a system works. So it's often used as a first step before building quantified simulation models. I don't do that, but others in the field do. And these issues arise just about everywhere. This is not at all limited to my field of business or to diseases or anything. These things just happen all over the place. And why we need system dynamics is that spreadsheets and regression methods simply cannot handle this. They are not fit for purpose. The business field I come from, all of the management theories and principles, not all, but a very large fraction of those emerge from multivariate regression analysis on large samples and so on. And it's hopeless. It doesn't tell you anything about how a business system actually works. And we'll see shortly why a spreadsheet it cannot be useful enough to cope with the issues that I mentioned at the top of the slide. This is very widely applied in all kinds of fields. Oh, I forgot to mention something really important. and it's that little thing down at the bottom right-hand corner there. You can get these slides. You need to get these slides. I think the organisers are making them available on the kind of handouts system for this conference. They are not PDFs, they are the slides, the PowerPoint slides. So after this event, you'll be able to go through those and actually run the slideshow for yourself. The other thing I should have said is that almost all of that slide set actually is the demonstration for building the policing case model that we were going to talk about. So you can effectively give yourself the same tutorial that you would have had if we hadn't changed our mind what we're going to do this morning. Okay, so where do we get to? We got to here. So the first thing to recognize is that the problems that we are trying to tackle are about how things change over time. If the issue that you're interested in is not a question of how things are changing over time, then it is not a system dynamics problem, and some other kind of tool is appropriate for you. And there is usually a history, not always if you're starting a new business or if you're planning to make create something new, then you don't have any history. But in many cases there is a history. We've got a very, very short history for the COVID outbreak at the moment. That history is important. It's important for two reasons. First of all, it tells you how the system actually works. If you've got a history of information about various things, then you can put those things together and confirm that's how it works. And the second reason it's important is that history is already telling you where the future is going. So as of right now, the number of people who are out there infected with the virus is already determining the fact that tomorrow there will be more people with the virus. That we are on a trajectory. It's like steering a super tanker thing. You can change the direction, but you can't move suddenly to a new place. So you can see the examples here. Losing weight. Can we get the fish catches improved? Can we eradicate polio? Can we get our bank balance back above zero? Can we cut the crime rate? That one, the middle one at the bottom there, is what we would have done with a particular type of crime on the London transport system if we followed the tutorial.
Could I just throw in another analogy outside of your solution? If anybody's ever tried to play ping pong with a basketball,
right?
You with a ping pong ball, you can change the direction, pretty instantaneously. There's a bit of momentum there, but playing with a basketball, it's pretty difficult to alter the course, and the history is basketball coming over the net.
Right, indeed. Yeah, we are rather trying to play basketball with a table tennis bat on COVID right now. So that's what you commonly see when you're looking at a problem, and the future could get worse. The situation could continue on the bad trend that you don't want, and it will take some time to fix. What we're searching for is, what do we have to do to move from the red line to the green line? And we'll see that there are some pretty scary red lines on the disease thing. So let me tell you about modeling infections, the basics here. Essentially, the whole population starts out susceptible to the disease, and a very small number of people catch the infection and become infected. So catching the infection is an event. Being infected is a state. So there are a certain number catching the infection per day, and each day there is a current number of people who are currently infected. And you can see the numbers being reported on exactly those two things every day, both in the UK and around the world. Those infected people then contact other susceptible people and infect them. And what that does is it initiates exponential growth of that infected number. So the more susceptibles they contact each day, and the more infectious, the more contagious is the disease, the faster is that exponential growth. After some delay, infected people recover and they become resistant. That means there are fewer people who are infected and therefore available to continue infecting other people. At the same time, the disease kind of runs out of susceptible people to infect. So if you're infectious on day one and you go out and meet 100 people, you could infect all 100 of them. After 3 months, when you go out and meet 100 people, it could be that either 80 of them either are themselves already infected, or indeed that they've become resistant. So there's only 20 people left for you to infect. So what happens then is that slows down the growth of the disease. This is a hugely widely known structure in the infectious disease field. It's called the SIR structure. You may hear people refer to the SEIR structure, where the E refers to people who have been exposed, but who are not themselves yet infectious. Yeah, they are infected, but they're not infectious. So that's what SEIR means. Oh, by the way, if anyone on this call knows more than me about disease modelling, please do put your hand up and jump in and correct me. I'm no expert in this at all. I'm getting slightly more expert as each day goes by, but I'm not currently an expert. So you are going to start on doing this. And to do this, you will need to get the software. This will be should be very, very quick and easy. Sean mentioned in introducing this that we developed a software called Systea for this purpose. It's a browser-based software, but Systea itself is now being substantially upgraded to this software called Sheetless. So this is what we need you to do. Go to sheetless.io. You should see that screen. Click on pricing. That should open up this screen here, and you should then select the community edition. So you can build one private project, and you can build unlimited number of public projects. So click on that to get started. And there are some tutorials where Sheetless is really quite new, so the tutorials are a bit in development at the moment. But if you click on that link there, don't do it now, but make a note of that link, sdl.re/sheetless-start. It's a little YouTube set. It takes you through the basics of that. It then switches over to some Systea videos, which it basically works the same way. So hopefully that will get you started. What you then do is, actually, I'm going to stop at this point here and ask you to, if you could start a poll now, asking people to let you know when they have successfully got to this screen.
Hi, Kim. Yeah, I will let them know. I'll create right now the poll. Quick.
If anyone gets behind, don't despair. The models are all available, so you may just need to sit back and watch and listen and take notes and raise your hand to ask questions. I won't be able to stop for every person on the call to catch up with every step, but I hope you'll forgive me if I press on.
Okay.
Yeah,
there's
so
the poll not working.
The poll and around 50% are already there.
Okay, The poll is not working for me. I don't know if that's a problem or not. I already have the
Oh
software.
yeah, it's because you're a panelist. It's just working for attendees.
I see. Okay.
But yeah, we have a 50%, around 50% yes and 50% no so far.
Still only 50.
Those of you who've answered no, that you're not able to do this, if you want to maybe put a comment in the questions or chat section to let us know what problem you're having. So one person's had an issue where Chrome wasn't working for them, so they're having to use Edge. Another person having...
It won't work in Edge. It'll work in every other browser, but not Edge. So Firefox, Safari, Microsoft have put some features in Edge that are very difficult for the software to support.
Thank you, Kim. That's really great. A few problems with the links. If myself and Diego will grab the links out and we'll pop them in the sort of handouts and chat section to share with everyone again.
I hope everybody spotted that is the link to go to, sheetless.io.
Yeah, I think people have to create a Google login apparently as well.
Shouldn't have to. Shouldn't. No, you should be able to sign up with just your email address and a password.
Okay. Well, we can figure it out as Jenny said, help people out with chat questions, and you can continue if you want.
Okay.
Yeah, some people are taking time in terms of the verification email. Just that's.
I really should apologise. I should have issued these instructions before. I didn't realise this was going to be so problematic. How are we doing on the poll? Have we got much above 50% yet?
Yeah, well, so I closed that one, and it was a 60%. We're done already.
Okay. All right. Well, I hope that they will be able to get on the software. If not, please just watch what we do and follow along. So you should you should see this screen when you actually successfully signed in for the software. And later on, your projects will appear to the right. You won't see anything just now because you haven't got any projects. Click on the New Project button, and let me just explain that a project is it is one or more models that share settings of various kinds. So when you've clicked on New Project, you should see this window. So in the name of the project, type in whatever you like. I've put my first infection model in there, but you don't have to put that in. Put a name in for the project. Put in some description there, and click the Create button down at the bottom right. Now, when you do that, you should see a model screen. What I'm going to do now is I'm going to switch over to the software and actually do that same thing. So I'm going to go back up to the dashboard. I'm going to create a new project. Click create. And this is the project's landing page. Could we do another poll, Diego, just to ask people to let you know when they've got to this page?
Sure. I'll put the poll. So the poll will be asking you if you have done this task. It's called task B.
Well,
now
yeah. Have you got to the screen? Have you got to the?
So 90% are saying yes.
Did you say 90?
Yeah.
Wow. Okay. So the 50% caught up. Fabulous. That's good. Excellent. That's really good. So this is the, as I say, this is the landing page for any project, and this is where you do things like saving copies or sharing, closing, deleting, that kind of thing. So you now click on the open button, and you now are in the project's first model itself. Now, the first thing we need to think about in any model is over what timescale we think things are going to change. And for our infection model, the model we built, we're running it currently over 180 days, but we could make that 360 days, make it a year if we want. And you do that in the project settings at top left, project settings, and I'm going to make that 180. Now, before I press on with this, let me just say a word or two about what your choice of timescale and time units should be. Clearly, if you're looking at a very long-term thing, like, I don't know, some company's strategic plan over the next 10 years, then it's going to be a 10-year model. But you should always think about how much history you want to put into it. So that company might want to have, say, 5 years of history. Then there's a question about, well, what should the time units be? And it is very common in long-term planning things, not just in business, but in government as well, to do annual plans. So you'd have, in the case I just mentioned, you'd have a 5 years of history and 10 years in the future, and you would have your model would go in annual steps. Now, in nearly all cases, that is just hopeless, absolutely hopeless. In almost every situation, things change much faster than that. So the thing to ask yourself is, over what time units do significant changes happen? And in most business cases that I work in, things happen on things of significance at the whole business level. I'm not talking about day-to-day kind of ordering of goods and paying people and that kind of stuff. I'm talking about big changes to the company overall in the kind of public policy context. If we're thinking about numbers of people going through schools or through normal health things, or going through the criminal justice system, you're looking at changes happening at the rate of monthly or even weekly. So you want to pick time units that are small enough that tomorrow isn't, that are small enough that the next point in time is not very different from this point in time, right? If you possibly can, the next point of time is not very different than this point in time. So what kind of time units do you think we need for this case? Yeah, I can make a case here for time units that are much less than a day. The problem, of course, is that we've got a time horizon of 6 months, and we're only getting information every day. So daily is about as much as we can do. This item on the right here, by the way, experienced people in the system dynamics field will know of a concept called DT, or time step, and it basically says how many times inside each time unit do you recalculate everything. So if I set that to 4, the simulation, the model would recalculate something 4 times every day. For our purposes, we're going to leave that at 1. So this is now a 180-day model, and what we're going to do is we're going to start with something called a stock, and think of this as a tank or a box that holds stuff. And the way we do this in this particular software, if you right click, you'll see all the things that you can add, and most of the things you add will be things called variables. All right.
Sorry to interrupt, but this is an issue that I've had personally. I don't know whether it affects anybody else, but I can't right click on the software, so I have to use the shortcut keys.
Okay, good. Thanks for that pointer, Maurice. Yeah. Whether you can or whether you can't right click, a much quicker way to do all this anyway is just to hit the S key on your keyboard. So this is a stock, and as I say, think of this as a tank of people, and we're going to call this tank the tank of susceptible people. We're going to put a big number in there. Let's say 1,000, and it's just going to stay there. Okay, so what you're looking at here, this is a time chart going across the object. So there's the 180 days going along there, and there's 1,000, and we can put in here what we fear will happen. We fear that that number is going to fall sharply because those people are going to get infected. What did I just do then? I just clicked with the mouse and dragged it down. That's all I did. Okay. Now you can see both of those time series. Click this data button down at the bottom right, and the blue line currently is the simulated line, and the red line in here is we call it the sketched time series. What you can do if you've got actual data is you can get it from your spreadsheet and just paste it into that column. Now, why do we need that other data series? Well, we need that other data series because the whole point of building these models is to explain what we observe in the real world and tell us how we get to the future that we want to have happen or that we fear will happen. So think of that sketch series as what's happening in the real world, and think of the simulated series as saying what is the simulation telling us about how the real world might be behaving.
Kim, one more thing, just to mention, next to the word susceptible in your stock, there's another open box there. We've been using that to document the units on the stock. So I put people there, but you know, it's very, very important to keep track of your units in these things because it can otherwise produce wacky behavior if you don't keep your units straight.
So over here on the desktop, you can see that stub. It's just a little bit of text that kind of shows up below the name. The other thing you can do and should do, by the way, is use the note to write documentation about where this information came from. Really, really important. So not only you, but other people can figure out what you've been doing. Okay. Now, over time, that number is going to fall because they're going to become infected. So what we need over here is another stock. So let's put S here for another stock. And this is infected people. And if you don't put anything in there, that starts at 0. So I won't bother putting 0 in there because that's what it starts at anyway. And what we fear will happen to that is that it will increase over time, and then you remember I said that it will go down because eventually people recover. So we think that something like that will happen. So how do we get people from susceptible to infected? Well, they are going to go through, as I say, think of this as a tank and think of this as a tank. How do they get from that tank to that tank? They get there by going through a pipe. And a pipe in system dynamics is called a flow. So we put a flow there, and we can move that flow around. And what that does is it pulls people. So grab on the back end of the arrow there, and you can move that around and pull it until it sticks to the tank. So now if I move that around, they're kind of stuck together. And do the same with the arrow head here. That's the head, and that says, "Ooh, I'm going to this pipe is going to carry people from that tank to that tank." You can think of this as a pump on that pipe, and that too has got a name, and that is going to be the number of people who become infected, and that has got to be in people per day. It is always, always, always the case, no exception ever, that the units for a flow are the same as the units for the stock per time period. Always. There's never any exception to that rule. So what we can now do is say, well, what happens if that infection rate follows a certain track? So what would happen if the infection rate did this? Well, not very much. You can see almost nothing has happened to the number over here of susceptible people. There's still 971 of them, and only 29 of them have become infected. What happens if it goes rather faster? Well, still almost nothing. Change the scale of this chart and see what happens if you get it faster. Oh, well, I've got some nonsense here, haven't I? Because I've actually managed to make the stock go negative. That could never happen. Now, just have a think about the numbers here. We're ending up at something like 50 people per day, and over the last what's that? Say the last 100 days, we've been going at something like 40 per day. 40 people per day for 100 days is 4,000 people. That's why it's gone negative. Oh, look, yeah, 4,000. That's what I just said. So that's clearly nonsense. But if we don't like that, let's just change the scale. We can fiddle around with this until we get something that would explain what we observe. So we're getting quite close to explaining that pattern that we feared for the number of susceptible people. Right, so now we're going to get the model actually to do something itself. How do people get infected? They get infected because they contact other people. So somewhere up here, slightly to the right, right click on a variable, or much easier, just hit the V key. This is going to be contacts per day per person. So when you go out in the morning, how many other people do you come into contact with during that day? And contact with in the sense that you get close enough to them that if you had the disease, you could pass it on. And we're just going to put a number in there. Let's put in, let's make a number up, 5. You can see that there's a time chart for that as well. This particular thing, we don't actually need that time chart because it's just going to be a number. So you can click this toggle chart, and that will make that go away. So on any day, how many other people do these infected people contact? Well, we could put another variable here. The other thing we could do is we could copy this one, Control C, and put it here, and Control V. You can move its name around by just dragging that. This is going to be total contacts per day. And again, you can put some explanation in there. And how do we work that out? Well, I don't think we need to be rocket scientists to figure out that the total number of contacts that these people make, actually, we do need to put some documentation in here, don't we? Because this is contacts per day by infected people. Yeah. And how do we calculate that? Well, it's going to be the number of infected people. Just click on the item itself, and you'll see it gives you a choice of things to put there. Just hit the enter key to select the one that it's come up with, multiply it by, and click on the next one. Now that says that by the end of the simulation, these 600 people are in total contacting 3,000 other people during the day. You'll notice that number is way more than that number. So I think we should perhaps rename the slightly total potential contacts per day, because they're not actually going to succeed in contacting that number of people. Why not? Well, because there is only a certain number of susceptible people left. So up here we need the actual number of people that these people can contact is going to be the fraction of susceptible people who remain. So I'm going to show you something else now that you often need to do. Over to the left, a variable, and call this total population, and give that a value of 1,000. We don't need the chart on that, and that is going to set the initial number of susceptible people. And we go into susceptible, and instead of having 1,000 here, delete that and click total population. Okay, it's the same number, but we need to know this number for the thing that comes next. And the thing that comes next is the fraction of susceptible people. And that is simply the number who are susceptible divided by the total population. Oh, I hope everyone followed the very basic thing I did here. When I link things up, you move the pointer close to the object and you see this grey cloud show up, and then that initiates a link arrow, and just drag it until it hits the thing that you want it to stick to. And that is going to be the number of susceptible people divided by the total population. So you can see, as you'd expect, that that's started at 1. So we start with a fraction of 1 for the fraction of people who are susceptible, and that falls to about 40%. So what we now can work out is how many of these contacts each day are actually with susceptible people. Maurice, I hope I'm going right here. I'm not making a mistake, am I?
Looks okay to me so far. Keep going. This is where epidemiologists come in. I think, you know, you have to try and work out what is the probability of somebody who's susceptible to being infected. And when there's a very small number of infected people, the probability of encountering an infection is low, but the probability of somebody being susceptible encountering them is high. And these probabilities move over time. As the infected population grows, the probability of encountering one grows, and the number of people who can be subsequently infected shrinks. So this is where a little bit of background in probability and statistics is helpful. It's conditional.
Go on.
It's just classic, conditional probability calculations.
Right. So of those total potential contacts, only that fraction, so it's that total potential contacts multiplied by that fraction, is the number of contacts per day by infected people. You can see that the variable names can get as long as you want. You don't really want to get terribly long if you can avoid it. But it does pay to have really nice descriptive variable names here. So we've got this number of contacts with susceptible people. So basically, I'm saying some of these people are getting in contact with more than some of these people. Susceptible people are being contacted by more than one of these people on any particular day. So it's perfectly possible for this number to go above 1,000 because it's because of kind of multiple contacts that go on. So what we now need to figure out is, of those people who are contacted by infected people, how many of them actually catch the disease? So we're going to need to make some space here and put some more space there. And we're going to put a variable here, which is fraction of contacts.
Kim, it might be useful to show people how to move things around on their screen in case they started too close to one edge of the work area.
Okay. Good idea. Let's do that.
Which highlight everything and grab onto one of the elements.
Okay, if you want to move more than one item, drag around it and click on the item itself, one of the items themselves. If you click on this, you'll just move the name around, all right? Or if you click on that, you'll move the chart around. So click on the object, on one of the objects itself, and drag it. So if you want to move the whole lot, drag around the whole lot, or Control A will select everything, and then you can move everything around. You probably spotted as we go that I've been tracking these charts around as well. So let's say that 10%, so a fraction of 0.1 of contacts result in the susceptible person becoming infected. Don't need that chart either. So now we know that we have this number of contacts per day between susceptible people and infected people, and we know that this fraction of those contacts result in someone getting the disease. So instead of this, remember we did this chart with sketch thing, didn't we? See that red line as I move the mouse around? That's the sketch line there. But what the software is doing at the moment is it's saying, you haven't told me how to work out what this number is. So I'm simply going to assume that the simulated numbers are the same as the sketched. Okay, that's what the software is actually doing. It's saying to itself, you know, you're not giving me any information, so I'm going to assume that the simulated number is a sketch. What we're going to do now is we are going to tell it what the number is. And we're going to link those together. It's down below. And that number of people who become infected each day is the number of contacts that happen multiplied by the fraction who get infected. What have I done wrong, Maurice?
I don't know.
Always useful to have a back button here.
I think you need to seed the infections here, because right now you're starting off with 0 people infected.
Of course. Oh, dough. Silly me. Yeah. So thank you for that, Maurice. A rookie error there, a rookie piece of ignorance on my part. If this number who become infected depends on the number who are infected, and when we start, that number infected is 0, then nobody can become infected. No. So
this
everything
somebody flying in from China and landing at Heathrow.
Exactly. Yeah. So you must all remember what actually happened here. What we had was so we got infected people arriving, and this does not need to be a continuous event. So what I'm going to show you here is something you can do. All the system dynamic softwares do pretty much the same as I'm showing you. What actually happened was that we had a pulse of people arriving when they came back from China with the disease. So we can actually actually we can do this 2 ways. Let me show you both ways of doing this. We go down to the data here, and on day 5, just put 10 in there. You can see the chart up there has given you a spike of 10 people. The other thing we can do is we can actually put in a formula that does the same thing. So a pulse of 10 at day 5. The kind of intuitive formula, pretty easy to do. And there are various functions like this that you can use. So the number of people who become infected in this population is now 10. Strictly speaking, we should come back them to the 1,000 people, but let's imagine that 10 other people caught the same plane out, so we've still got 1,000 people there. So the number who become infected is now, you can put line feeds in your formulae just to make them easier to see the structure of number of people that arrive plus. So now we've got those 10 people arrive, they joined the infected population, and look what happened. Wow, that's a really, really scary takeoff for this disease. We've got 5 contacts per day between these people. 10% of those contacts result in somebody getting infected, and we've pretty much hit 1,000 people by, what's that, day 30. So that just shows the power of exponential growth, and this is why politicians and leaders really kind of didn't get it for a long time. People are just not used to anything behaving like this. That's why they were all caught unawares and struggled. So we've got something that looks really very, very scary here. So how do we reduce this? How do we make this less? Well, one thing we can do is we can cut the number of contacts per day. That's what we've been doing. We've been cutting the number of contacts per day. If I reduce that number to 1, we get a much slower takeoff. If I reduce it to 0.5, oh, magic, right? 0.5 is the number that matches the scenario that we set out to achieve. Okay, I'm going to put that back to 5, but I'm going to do something else. If we look at the data here, let's have a look at the data. So we've got for this variable. So we've got up to 500 people. That's too many. We want to stop the infection earlier than that. When we get to 100 people, that's about time 12, we're going to cut that contact rate per day. So in here, we'll type in if time is less than, did I say 12? Then 5. Else 0.5. So you can see we were on the trajectory that was going to get us way up to all 1,000 people infected by about day 30, but with a lower contact rate, we've managed to push that back almost to the end of the period. There's one last thing to do to finish this model, and that is to recognise that people recover and become resistant. So over on the right,
Kim, just one technical point. At that point, it would be helpful, just so you know what's happening in the simulation, to toggle the chart in for the contacts per day per person.
Ah, yes, it would. Very good point. Yeah, we need to see that, don't we? Otherwise, we will have forgotten what's going on here. Okay. Right. So we'll have some resistant people over here, and that's going to be another stock. And that starts at 0. We're going to add another flow, and that flow is going to be the number that recover per day. And we're going to make a rather simple assumption, which is that when you get this disease, you are only sick for a certain number of days, and then on the same number of days for everybody, you recover. So that means that the number who recover each day is the number who become infected each day, but add a variable here for days to recover. Let's say that's 14. So how do we work out this number in here? Well, it's going to be the delayed number of people who become infected, and it's going to be delayed by the time it takes to recover. I mean, notice we've now got a very, very different pattern on the infected number, because after those 14 days, people simply move out of that state and over here, and then no longer available to infect these people. Let me put this back to just 5 per day. So we can do that, change it, the alternative value to 5. If it's just 5 per day and it takes 14 days to recover, then yes, we do get up nearly to 1,000 of people infected at any time, but they very soon move out over here. If that contact rate were, just take that out completely. Another useful thing for the note, by the way, is a temporary parking space for your formula. I'm going to put that back to 2. I'm also going to make the infection a little bit less contagious, so only 1 in 20 of those contacts result in you getting sick. So I'll show you one last trick here, which is that you can set up scenarios for different assumptions. So we're going to add a scenario. So click on the left over here. You can see blue says base case, and the blue lines tell you that's the base case. We're going to manage scenarios, add a scenario, and we'll call this less infectious. Call it anything you like. save that scenario. And if we click on that, you get another view of the same model, and you can see all the numbers are now gone red to match the color of the scenario. And that I mislabeled that, didn't I? That should not be less infectious 0.1, it should be less infectious 0.2. So you can now change. What you can't do in a scenario is you can't move anything or change any calculations. What you can do is you can change values of things. So in this scenario, this is going to be 0.02. And we are actually viewing that scenario. And that may look a bit surprising, don't you think? We've got 0.5. And that gives us a huge takeoff in infections, and you know, an awful lot of people end up. This is with contacts per day of 2, factor 5. But if we look at the less infectious case, we don't get that. Right? We don't get everybody infected. Maurice, is this what we call herd immunity?
I think so. I'm actually having trouble replicating your result here, so I'm trying to figure out what I've done different. I think it's you have 5 contacts per day in the scenario. Okay.
Yeah.
Yeah. Okay. And also these little eyes that you use to show what's happening in each case, switching them on and off is something that you didn't explain.
Okay. Right. So if we look at the base case. The base case is what you see. I can also show the less infectious case with the little eye there, so it just shows that time series as well. So let me put another scenario here, which is more infectious, 0.1. So you need to click on the scenario, so you get the colours matching the in the item there. Instead of 0.05, that's going to be 0.1.
Kim, I'm afraid if anybody else is like me, I've managed to get out of sync with you on the parameters. So just in case that's happened to anybody.
All right. Well, let me just take you around those parameters. So
starting on the base case, perhaps.
The blue base case, click on base case. You should have 5 contacts per day per person. You should have a fraction of 0.05 of contacts ending up getting infected. You should have this pulse of 10 people arriving on day 5, and you should have 14 days to recover with this delay. So we're now at 11:15, and I don't know about anybody else, but we must be getting ready for a break. Let me just say a couple of things before we have that break. The first is when you build these models in your browser, the model is always currently saved in your browser. You can go away, do all kinds of other things. You can close your browser down. You can almost certainly, I think, close your browser down. You can restart your computer. All kinds of stuff, and the model should still be there. Under project, if you click save project, what that does is it saves a copy of your model to the server in the account that you created in the first place. The other thing I'd just like to say is that you may remember we mentioned at the beginning that you can't do this kind of stuff with spreadsheets. Well, that's not strictly true. Technically, it is possible. So what are you looking at here? Think of this diagram as being a picture sitting on top of a spreadsheet, and every one of these items is a column in that spreadsheet, and it's got its values starting at day 0 and going down to day 180 down all of the cells in the column. Now, if that is a, let's pick the less infectious scenario, so we've got a number there. So if that is the number that we end up with at the back end of the scenario here, there's a whole column of values for that item going all the way down. If you go all the way down to 180, you should end up seeing that. No, that's not what you're seeing. No, I don't know why that is. That's because this is showing the base case. That's why. So that's the number that you end up with in that scenario. It's a column in the spreadsheet. That is this thing is the column heading in row 1 of your spreadsheet, and all the values go down. What are these things then? What are these links? Well, they're just cell references. So if this is column A and this is column B, then cell B1 equals cell C1 is cell A1 multiplied by cell B1. That's all it's doing. There's nothing magical. There's no kind of fancy maths going on here at all. It's just arithmetic. And in fact, we can show exactly that by hitting right-clicking and creating a table. And I'll just hit T on my keyboard. I can drag a link from infected people into there. I can drag a link from contacts per person per day into there. I can drag a link from there. And guess what? There is a spreadsheet with the numbers in your model, and you can copy those columns out, you can put them in a spreadsheet, and you can replicate exactly what this model is doing. The other thing you might want to do is see some of these things together. So let's put the number of infected people in there. Let's put the number of susceptible people in there, and let's put the number of resistant people in there. And it shows you each of those charts. And if you've got a sketched chart for a sketched set for any of those, you can see that as well. So now would be a good time to save your project, and we'll come back afterwards and talk more about the actual COVID model. When are we going to get back together again? Let's get back together again at 11:30.
Thanks very much, Kim. Just to comment, what I will do is I'll unmute attendees. Obviously, it won't unmute attendees' mics unless they choose to do so. But if people want to pose any questions to Kim right now, is that okay for you, Kim?
Yeah, do. Yeah. In fact, why don't we? You will go and have a break if you want to. I'll stay here and answer any questions.
Oh, that's very kind of you. So participants, attendees should have an opportunity to unmute themselves should they like to have any discussion with Kim, or if anybody wants to run through what they've built versus what Kim's shown.
Yeah, if someone wants to ask a question, can they raise their hands so we can unmute you?
I have a question, Diego.
Who's this?
It's Maurice. I'm a panelist. I don't know how to raise my hand.
Okay, yeah, we have a couple of questions also. Yeah, you want to go first?
No, I just want to know how to raise the hand.
Okay. I think as a panelist, you cannot do it. You only if you're an attendee.
Okay,
So
all right. Questions, then? Don't be shy about questions, by the way. There is no such thing as a stupid question in this field. If you don't understand something, you can guarantee that somebody else doesn't understand it either. So
thank you, Kim.
Any question you like.
One comment to all, my apologies, the functionality that allows me to unmute you all automatically seems to not be releasing at the moment. So those with hands raised will go through in turn. Diego, are you happy to take people in turn with the hands raised?
Yeah, I
Thank
think,
you.
yeah, I can, let me,
Oh, it's rather a shame that we can't unmute everybody. It would be really good if we could unmute everybody.
oh yeah, I think some people are self-muted. So now I think Steve has a question. If you unmute yourself, we should be able, just make sure.
Steve appears to have gone away momentarily. So if we move to David, who's showing as active. David, did you have a question?
Done what we said and gone to get himself a cup of coffee.
Very true.
Hello, Kim.
Hi.
Thank you for the introduction. I notice that in your definition, ST is a quantified modeling activity. How easy is it to get the data from groups rather than individuals? And do you see this software as a way of contributing to that by people having different sketches of the relationships?
Thanks for that question, David. Yeah, we are relatively lucky in the case of this particular disease that a lot of effort is going into collecting numbers as we go. So we know how many new cases per day are confirmed. We know how many people die each day, and so on. But even in this case, there is a lot going on that we just do not know. We actually don't know what those contact rates between people are. We do not know how contagious the disease is. If you get in contact with someone to the degree that you could catch the infection from them, what is that fraction over there? And in other situations, there are many more unknowns than that. So what do you do? This is where the process I mentioned at the beginning comes in, the Agile process. You start with what you do know, and you drill back through the causal relationships between things, putting in other numbers that you know, and if you don't know, putting in what you think they might be. So if I wanted to explain why that red line resulted, I would have disconnected that thing there. So what does this have to do to give me that red line? And say, well, yeah, and then you go back to the next item in the causal relationship and ask the same question. But you do often find that, particularly in cases where there are lots of intangibles going on, lots of soft variables like how strongly people feel about things and so on, that people have got very different ideas about what those numbers might be. So things like this, where you can put in different scenarios and play out the results of those different scenarios, is a way of saying, well, Jane thinks it's 2 and Joe thinks it's 4. Given what we do know, which of those estimates is more likely? Yeah. So definitely.
As an example of that, in this COVID-19 crisis, we're putting a number in for contacts per day per person, but that's a result of a government policy based on perceptions about how effective they will be, and it embeds cultural differences and how compliant people are with what the government says. So a total lockdown in Greece resulted in everybody going to the beach and intermingling with each other. So they had to shut the beaches down. And so the policy, you might have made an assumption that total lockdown would lead to very low contacts per day, but there's a weak relationship between what the government says and what people do. And on the other hand, here in the UK, people were more compliant. So there was an intangible relationship between the government and the people.
Any other questions?
Yeah, we have Steve Birdshill. Let me see if he can talk right now. Steve, can you ask your question? I think he's self-muted at the moment. If you just unmute yourself, you can ask your question or write it down. Okay, if you just write down your question, I can read it to Ken.
I'll wait, yeah?
Yeah.
Can you hear me?
I can listen to it, yeah.
Great, my background is human factors, and it brings in certain aspects of modelling. And my experience to a large extent is that most of this simulation can be done principally without human intervention. Most of this can actually be automated with particular programs that can just overlap, override, over-elaborate principally what you're doing quite meticulously. You did declare that it's not fundamental mathematics, it is more arithmetic. But that, basically, it seems to me that you're kind of employing something which is speculative, and you raise the point, and quite efficiently so, that you don't know how this epidemiology is going to ride out. But there are various, and it doesn't take much investigation to realise that epidemiologists do use a range of models that can automate and process and project literally the protection of the infections. And it seems to me, as I say, that because you're employing to some extent largely speculative arithmetic, I'm trying to fundamentally understand where this human side that you're employing and the speculative side really makes any kind of reasoned sense. I'm sorry if that sounds a bit kind of broad approach, but I'm very familiar with a lot of kind of simulation methodologies, which this one, as I say, relies upon a lot of kind of personal intuition, which is not necessarily how epidemiologists model this kind of infection rate, and there are and is and quite elaborate understanding of how this is going to play out, and that's why people do take necessary steps and why necessary interventions have been put in place. To actually speculate by looking mathematical formulas, arithmetic formulas, to suggest how this is going to play out is not really relying upon what the modelling software is capable of doing, automating beyond this kind of human intervention or human suggestion. So just out of interest, is the software, I posed the question before, with the principles you claim are transferable, but that, to some extent, it seems to me that you're working with a piece of software which is not really the kind of thing that at the highest level of simulation would be employed.
Well, quite a lot packed into that question. The SIR, the maths of the SIR structure is what epidemiologists use. We're not doing anything here that is any different than the very most basic SIR mathematical model that epidemiologists would build. The significant difference is that we're making everything visually explicit, so that you can see why things are playing out the way they do over time. Now, in their SIR models, there is a concept called R0, and R0 is the number of people infected by each infected person. Okay. Now, what that bundles together is how many contacts per day each infected person makes, how contagious the infection is, and how many days people are infected. So we can actually calculate or in this model. At least I could have didn't want to do that twice. So let's calculate R0 here. R0 is the number of contacts per day, the fraction of those that cause another person to be infected, and how many days the infected person remains infectious. So that times that times that, 3.5. That is a number that the epidemiologists talk about all the time. And they point out that, you know, if that number can be got below 1, the disease dies out. If it stays above 1, the disease escalates. But that's a concept that's in their models. Sure, you can, and we'll show you after the break that the models can be very, very much more detailed and complex than this simple example I've shown you. But there's nothing fundamentally different here than that is in the models that the experts use.
Can I ask something to that? Or?
You could. Can we just check if there are any other questions first?
Yeah, please go for someone else.
Yeah, yeah, we have Rachel Nguyen. I'm gonna unmute her.
Okay, Steve, while we're just taking other questions, feel free to put your question in the chat, and perhaps somebody can make sure I don't.
Shall do. Thank you. Thank you. Will do. Thank you.
Thank you. Thank you, Steve. So right now it's 11:30. You want to continue answering questions, Kim?
Yeah, let's carry on just for a few minutes.
Carry on. Okay. So Rachel, can you're unmuted? Can you ask a question?
Hi, Rachel.
Rachel, I think, or can you post it if we cannot hear you?
Let's move on to Miriam a second. Rachel, we can't hear you. If you can post your question in the chat section, that would be great.
Yeah, okay. Miriam, now you're unmuted.
Hi, thank you, Mike and Diego, for this very interesting presentation. I am a PhD year 1 student at Queen's. My supervisor and I are doing an SIR model for Kuwait. Thing is, Kuwait is working to evacuate its citizens now from all over the world. We entered the second wave now. It's around 2,700 evacuees. So I'm wondering if I should add this number to the susceptible population, or people arriving, and another variable. What do you think about that? Thank you.
Well, if you're going to bring people back in, here's a way to do that. We have another flow here, which is people returning today, people. And you can simply put into the sketch time series however many you think. So if you think that 50 people are going to come back on day 8 and 100 people are going to come back on day 10, you'll see that those people have indeed come back here, and in our base case scenario we've now ended up with 1,135 people resistant, and we've still got 15 susceptible over here. So add those two numbers together, and that's the 1,000 we started with plus the 150 who returned. So that's how you do that.
All right, so that variable will flow into the infected people arriving, right? Or the
if they arrive infected, then yes, indeed. That's that's this thing here. I simply took 10 people out of there into there and said that 10 people arrived and 10 people left, so that my total was still 1,000. But if I took that away, in fact, let me do that, so that instead of that happening,
okay,
it's the return of those people that causes the infection to happen. So let's go.
You need a fraction of those people who are infected, because perhaps they may be asymptomatic and yet infectious and all kinds of nuances like that.
Yeah, so if that, so we would have a variable down here for total people returned per day. We'd have a flow like that. So this is infected people returned per day. We'd have another flow over here for uninfected.
I see.
And then you'd calculate the fraction of I won't do it now, so we can move on to other things, but you have a variable down here for the total number of people. You have a fraction of infected, and you calculate this number from the total and the fraction, and you calculate that as 1 minus the fraction.
Kim, would it be worth mentioning to Miriam that we're offering a framework for her to use if she wants to?
Yes, the project that Maurice dragged me into, screaming and shouting, not really. Actually, its purpose is to provide a model that can be configured for any particular country or contiguous region. So that's what we did, what we've done, and we will show you how to get at that model.
Perfect. So will you share it at the chat, the question sections, or?
We'll give you all the details in the second part of the class, which we should start actually. Any more questions? Any more burning questions before we start up again on the next bit?
I think Rachel, you can speak or post your question, but she's not answering. If not, there's just one question more from Steve as well. So he asked if economists largely describe as unnecessary to use beyond basic algebra to model projections. Econometricians are seen somewhat as technically astute but misplaced. If you could extrapolate.
Oh, okay. Well, it comes back to the question that we started on, which is that all of the relationships in here are essentially simple. There's nothing very complicated or mysterious going on in any of this. It's when you put them together and you get these accumulations happening over time, and you get these feedback effects here, so that there is a reinforcing feedback here. The more infected people you have, the more new people become infected. We have balancing feedback going on. The more people become infected, the fewer people remain to become susceptible. So you've got accumulation, you've got feedback, and the combination of those things. Although in theory you could write this model in a spreadsheet, you could just copy all this stuff out and put it in a spreadsheet and prove that to yourself, probably in less than half an hour. You cannot conceptually handle that. You know, the human brain simply cannot do this kind of two-dimensional, multi-interdependent stuff and get it right. That's why we need the software. If you add into that mix threshold effects, so in many cases a variable might be increasing. Let's say it's the number of people arriving at hospital with COVID, and as long as that rate is less than the number of available spaces in the hospital, they can be admitted to the hospital and they can be treated well, and some of them will recover and some of them will die. As soon as that arrival rate passes a threshold, that's when all hell lets loose and the health service can't cope. That's a threshold effect. So we've got accumulations, we've got feedback, we've got threshold effects, and we've got intangible factors as well. People's confidence, people's acceptance of the requirements to stay at home. Do I stay at home or do I go to the beach? That's an intangible state of mind that affects things. So that's why we need these things. Even so, from Steve's question, the relationships are still essentially relatively simple. They can be expressed in simple arithmetical terms. We don't need. You may have come across a concept called Occam's razor. Occam was a 13th century or something monk or religious person who came up with a guiding rule of thumb, which is that given a range of possible explanations for something, the simplest and most concrete is probably correct. If you prove that it is not correct, then by all means go on to the next most tangible and the next most simple. But until you've proven that the simple explanation isn't good enough, don't assume abstract things and don't assume complicated things. And what economists look for is what econometricians look for is they look for statistical relationships between things. So is there some statistical relationship between, this is not a good example, but let's say unemployment and crime rates. Well, there may or may not be a statistical relationship between those things, but if you want a causal explanation, you've got to go through these relationships that are actually happening out in the real world. I've been accused of being kind of ultra realist in my approach to life generally, and certainly my approach to building models. I am always looking for what is really happening here. If I can't go out and see it and touch it and measure it, then I remain to be convinced that the thing exists. Including intangible factors, by the way. We can detect and measure intangible factors. Okay, are we ready for part two, or are there more burning questions?
No, you can continue, Tim.
Okay, right. Let's get back to this. Sorry, I just heard something saying I was muted. Is that right? Have I been muted or unmuted?
You're unmuted.
I'm unmuted.
Yeah.
Sorry, I think I was just being offered a cup of tea, which would be extremely welcome if that's possible. So this is a more developed SIR model. Thank you. And it has a couple of other features that we've included in it. One feature is this link down here, where it allows the possibility that a new strain of the disease emerges. And what happens when a new strain emerges is that everybody who was resistant suddenly goes way back over here, becomes uninfected, and the whole thing starts off all over again. Here's our contact rates and our infectious rates, our infectiousness fraction, and here's the second burst of new people becoming infected. The other thing it offers is the ability to do two things. We can actually tell people we are going to restrain contacts, and we can set a point at which we impose that rule and see if that helps. The other thing we can do is we can actually vaccinate people. So I hope this is going to work. I will go to that model. Here is that same model, and I think it's a slightly different set of values than I showed on the slide, but it is that model, believe me. And what we can now do is start. It's also got some nonsense in here. It shouldn't be possible for things to go below 0. I don't know what I've done there. Some silly mistake. I don't know. I've made some silly mistake, so I'll try and fix that. But first of all, let's slow this thing down a bit. So let's say that the percent of contacts infected is only 10%. So you get a slightly slower progress of the disease. But let's say the government now says, well, we're not having this, we're not going to allow this to happen, and we are going to. So this is the normal contacts per week per person. So in this scenario, the normal person contacts 20 others per week. This is a weekly model now, not daily, right? So it's 20 per week. So what's that, about 3 per day? So the government says this: we're not having this. We're going to, as soon as they see the number of infected people reach 5% of the total, the contact rate is not 20 anymore. It's 0.5. The other thing that is a bit different in this version of the model, I'm sorry, this is an update of the model I just showed you. I'm sorry. We've now separated people who know that they are infected and choose not to be in contact with other people quite so much, probably because they simply choose to stay at home in bed until they get better. So nobody's telling them to stop contacting other people, they're just doing it anyway. These people are infectious, but they don't know they've got it. So they're carrying on contacting people at the rate of 20 per week. But the government says to everybody, these people cannot go on contacting 20 people per week. They can only contact 5, and these people continue contacting 5 per week. So let's cut that down to 2. And if we cut it down to 2, guess what? We keep everybody safe for a very long time. What we've effectively done is we've dragged that R0 number for this disease down below 1, so that the disease grows for a while, but then it simply dies out. If you do go to this model, by the way, I think the one I actually showed, I explained right in the beginning that you actually get a project in your account, and a project can hold more than one model that shares the same settings. So I think the one I may have shown you here is that. Yeah, there we go. That's the one I just showed you on the slide, where we're not separating out the infected people into unaware and aware. So if you do go to that link I showed you, you will get all these models that you can work with.
Kim, when you were talking about that, you were on mute, so it might be worth just jumping back there one more time.
How did I? Sorry, has no one heard anything that I've said since the end of the break?
No, you came in right after you introduced the links. You were highlighting them, but I couldn't hear it. I don't know if anybody else could.
Oh, okay.
I think I could hear. Maybe there was a problem on your end, Maurice. Let me just check.
I could hear.
Okay.
Okay, right. Okay, right. I was just being given some audience feedback there about how it's been going. So everyone has seen and heard about that link up there. If you go to that link, you get this project with these models in it, and the one that corresponds with the slide is this single infected group model. So there we go. Right, I need to go back and give you a bit more of the principles of this stuff here. We'll come back to this shortly. This is the COVID model. Actually, no, let's go. Yeah. I'm sorry. Changing the plan today has left me a bit disorganized. I apologize for that. So let me just set this in the context of the wider approach to building system dynamics models. You may come across these things called causal loop diagrams. I mentioned at the beginning that this is a qualitative approach to mapping out how people believe things are related to each other. you may, the diagram is called a causal loop diagram, and the approach is sometimes called feedback systems thinking. And the word feedback on the front of there is really rather important, because there are hundreds of other approaches that call themselves systems thinking. So this just is more specific to this particular approach. And what that says is that the more infected people you have, the faster more people become infected, and that gives you a reinforcing loop that will generate accelerating growth. This thing down here says that the more infected people you have, the fewer uninfected people you have, and that will slow down the number of infected people you have. That's a balancing feedback that will slow growth or decline. And put those two together, and you get the kind of S-shaped growth pattern that we've actually simulated. So the fundamental components.
Just a quick question, Kim. There's Colin Elgid is asking what are the assumptions in testing, and how is the actual number infected visible versus the number reported?
Sorry, is that question relating to the model itself? The simulation model?
Yeah, I think it's to the model. Yeah.
Okay. When we come back to the COVID model, we will show where the data is that relates to confirmed cases and unknown cases. So we will demonstrate that when we get back there. Yeah. Perfect. Okay. So the components of the system dynamics method, everything should have time charts on it. Everything that changes over time should have a time chart on it. So it might be deaths per week. Always specify items clearly and define their units. Always specify the scale of the item that you're looking at. Always specify the time scale, and always show how values have changed or may change over time. A very common thing that people do when they start building system dynamics models is put lots of things on the screen with lots of links between them. Oh yeah, I'm sure that this causes, I'm sure that A causes B, B causes C, C and D cause F, G and H, and by the time they get to Z, they've got 26 items on the screen, none of which have got any data in them, and none of which have got any calculations in them. That is the path to disaster. Do not do that. Do not ever do that. Always put time charts on anything that's changing, and always put values in those time charts or calculations in those time charts, even if you have to estimate them. You will need to highlight the fact that you have estimated them, put a big red box around them or something, say this is just a guess or this is an estimate. But you should always have a working model. In the method, these arrows always mean that if I know A and B, I can work out C. Now, in most cases, what I mean by I can work it out is I can actually calculate it. In many cases, though, you can only estimate what B is if you know what A is, and the software we're using, just like all the other softwares, allow you to capture those kinds of estimated relationships with something called lookup functions. So
can I offer an example of that in this case? There's a research conducted by Imperial University, Imperial College rather. They produced a benchmark for what was going to happen here in the UK, and they relied on some research out of China on how many people recover and over what time period, and how many people die and how quickly. And those two relationships, somebody becoming infected, is going to lead to either a recovery or a death, but it's highly uncertain exactly how long it will take, and it's a probability distribution.
Right, and you would put that in as a lookup table in the model. I don't think we'll have time to actually demonstrate that, but maybe it'll come up. So the next component of the method is these things called accumulating stocks. I've explained all this, that as we went through building the model, and there are plenty of very common examples. Your bank balance behaves like this. So the symbol is a tank holding something useful. The numbers inside it say how much of what is in the tank. The thing on the left is a pipe bringing stuff in, and the circle on that pipe is a pump pushing more into the tank, and the label there shows what is flowing through the pipe, and the number shows how fast it's flowing. Those are the components of the method. This behavior of accumulating asset stocks, it is not a theory, it is not a statistical finding, it is a fundamental feature of how the real world works.
Kim, just one other clarifying point. You said something useful in the stock. You could also have a collection of debt here, which would be not so useful.
Right, yeah, yes, indeed, yes. I apologise for that. Yes, it's not always stocks of useful stuff. This stuff is useful. This is cash. It can be very, very kind of anti-useful stuff.
I can't talk right now. I'm actually a panelist in a conference.
Okay. So the other
right in 1 hour. Someone is asking about a business, more like a more basic business of this last cause and effect stock. If you could just give a really simple one. Some people are having a hard time understanding.
I'm not understanding the question.
So the question is, can you give an example of a business use of this where cause and effect can be more obvious?
A business example. Oh yeah. So all the work I've done is mostly in the business field, and when you're putting together a business model, there are some very, very standard stocks that you will find in pretty much every case. Almost every business has got customers, and you have customers that you win, you have customers that you lose. So the number of customers you've got today is the number you ever won up to today minus the number that you lost. The number of staff you employ is a stock, and the number of staff you employ today is the total number of people you ever hired minus the total number of people who you ever fired or whoever left the company. And the number of staff tomorrow is going to be the number of staff today plus the number you hire minus the number who leave over that day. So it's a completely standard set of relationships, and they all obey this rule. This is how the maths works, and it all works like that every single period of time. So this repeats every period. If you want a simple personal example, there's one in the first video clip at this link here. So can I give an example of a business use of this where cause and effect can be more obvious? I'm not sure. I hope I answered that question.
Yeah, I think it's a little bit more clear.
Okay. Now, given all of this, there is no explanation for the number in the stock other than everything that's come in minus everything that's gone out. So what that results in is that it is completely meaningless to try and explain the number in the stock as a function of anything else. So a kind of econometrician approach to this would be if I wanted to estimate what the bank balance of each person on this call is, I would go and ask them how old they are, I'd ask them how many kids they've got, I'd ask them how many holidays a year they had, and I would try and figure out a statistically significant relationship between those variables and their bank balance. And then I would then go away and say, well, I can estimate the bank balance of any other person by applying that formula that I got from statistical analysis. But I hope it is obvious that that is just a completely meaningless thing to try to do. this bank balance is precisely given by the sum of everything that was ever paid in minus everything that was paid out to the cent with 0 error term. So trying to explain the bank balance by statistical regression methods is pointless. And that has very important implications, because if you can't explain a stock's value with regression methods, you can't explain the value of anything that depends on the stock either. So you cannot explain, you cannot estimate what a company's sales growth is going to be, for example, by trying to correlate it with how much they spend on R&D or how much they spend on training, because between the R&D and the training is a stock of customers, and the sales depend on the number of customers, and you cannot explain the number of customers by regression methods, so you can't explain the sales by regression methods either. It's a meaningless thing to try to do. What is a stock and why should you care? An asset stock is a collection, group, population, mass, or volume of materials or entities that accumulates or depletes over time. Sorry, it's a rather long sentence, but that's what it is. And if you want to explain it to anybody else, there is a short article at this. This is a LinkedIn article at this link here. And it basically goes through an explanation of this thing and gives lots of examples. Their quantitative behavior is axiomatic. It simply is how the world works. And their quantities drive everything else in the system. So if we were to look at a university, for example, the number of classes per year that are given is the stock of courses multiplied by the number of classes per year per course that's given. That is just true. They are also important because they provide the memory of the system. So again, in our university example, the number of faculty lost last year will continue to affect our teaching capacity forever. And we can't undo the loss of those faculty. We could replace them, but we can't undo that event. You may know that UK national debt is currently somewhere around is it $1 trillion or 2 trillion? That debt is at the huge scale it is today because in 2009-10, after the last financial crisis, the debt tripled. The government had to increase the amount that it owed by a factor of 3, and that debt has continued to accumulate ever since. If that event had not happened in 2009-10, then we would not currently have a debt of whatever number of trillions of pounds it is. So no model of any kind can be correct if it doesn't recognise stocks behaviour. That's the bottom line here. They are that fundamental to how the world works. So what I'm going to do now is go back. I'm going to try to go back to the COVID model, and I'm just going to give you a quick look at the screen for the model first. Don't get horribly scared. This is the control panel on the screen. In the software I've just been taking you through, you have a feature where you can make one part of a model sit underneath another part of the model. So this is, if you like, the top level model, and it's not a model at all. Actually, all it's doing is getting information from the real model, which is sitting underneath it. So this is our COVID model for the UK, and we've set it up in such a way that you can choose to switch it to a second region of your choice and put data in for the second region of your choice. So we don't frighten the horses. We're not showing any of that kind of complicated set of arrows and things at this level. But what you have here is you have the number of susceptible people over time. You can see there's the 180 days, and this is what happens to the number of susceptible people. This is the number of confirmed current active cases in the middle chart, and the bottom chart is the cumulative number of confirmed cases. So the difference between those two is that the middle chart subtracts all the people who recovered or died. So this comes back to the question that somebody asked earlier: what are your assumptions on testing, and how is the actual number infected visible versus number reported? So we can only be told about the number of cases that actually are confirmed. The number at the top is the unknown number of people infected. Oh, sorry, that label is incorrect. That's actually the total number who are. When you get the slide set, you should make this correction. That is the number infected per day. So this item here is the number who are infected at any time, but don't know it. And you can see it goes up almost to the entire population of the country, because this disease spreads so rapidly. The scenario I'm showing you, by the way, is no control. We just let the thing go. We don't do anything to try to stop the disease. And over on the right, we've got the stock of people who have recovered. Below that, we've got the sad stock of people who died. You might notice, by the way, that you see the blue line there. The blue line is the actual data for people who have died as of I think about 3 or 4 days ago, and it is growing faster than this model is saying. Right. So if you think that's scary, right, if you think that's scary, almost everybody getting it and staying with it for some time and eventually either dying or recovering. The real world is scarier still, right? That's why this is such an awful situation we're in. This is the underlying model, and I'll just take you quickly through the differences. So the first thing is we've got a stock there in the middle of people who are incubating the disease. They don't know they've got it. They are probably not infectious. We don't really know. This is the people who are early, the early stage when they're infected, but they've got no symptoms. We know that the disease has this feature, that people are asymptomatic but infectious. We also know that many people continue to be unaware that they're infected, even though they are. Or they have such mild symptoms, they just think it's a cold, or they just think it's an ordinary bout of mild flu, and you know, they maybe stay off work for a day or two, but that's it. Then you've got people who are aware that they've got disease, but they only show mild symptoms. So, sorry, I need to just correct something I just said. The people in that stock don't know that they're ill, right? The people in this stock do know that they're ill, but they've got mild symptoms, so yeah, they stay off work for a day or two, something like that. Normal behaviour, basically. This stock is a stock of people who have severe symptoms but stay at home. And for those people, that's a very high death rate. And very, very sadly, that is a lot of people in care homes at the moment. Almost everybody who would be at home with very severe symptoms has taken themselves off to hospital. So these two stocks at the bottom are the number of people in hospital or in the ICU. This is adding up all the people who flow out of that middle column of stocks into and die, and this is the total number recovering. Up there we have the high contact rate for people who are unaware that they're ill. We have a lower contact rate for people who are aware and confirmed. Okay, so this is confirmed cases. And over to the left there, we have a mechanism that imposes social distancing for a period of time. Okay, so let me show you that actual model. Here's that control panel layer that I mentioned to you. And the way you use this model is as follows. We have the link to this model. I actually put it in the presentation. Diego's just put it on the chat as well. That will take you to this model. It's not locked in any way. You can do what you like with it. You can save your own copy. Basically, what you do is that you start at the left-hand side, and this item here tells the model whether you want to run the UK or another region. You change that to 2, and now the numbers will all be different.
Kim, sorry to interject. Just one thing that we wanted to really emphasize is the importance of localization, because this outbreak that we're facing is local, and the infection rates around London, for example, are much higher than outside of London. The infection rates in Lombardy are much higher in Bergamo than they are in the rest of Lombardy or the rest of Italy, etc. So when you're defining a region, it's very important to think about the region as a place where similar kinds of infection rates are happening, versus saying an urban versus an outlying area. And Miriam,
a really important point.
Yeah, Miriam mentioned that she's trying to model Kuwait, for example. It's possible, we don't know anything about Kuwait's experience so far, so this is entirely speculative, but possibly in Kuwait City, the conditions are quite different than they are in the outlying areas.
Indeed, yeah. So a good definition of a region to take is an area that meets the criteria that the number of people moving in and out of that area each day is relatively small compared with the rate of contact between people within that area. So to take an extreme example, we were talking to somebody on Crete a couple of days ago. There's almost nobody coming in and out of Crete. So that is a perfectly valid self-contained area. London itself is actually arguably not a valid self-contained area because of the millions of people who commute in and out of that area each day. An area such as Oxford, say, might be adequately bounded for this to be a valid thing to do. But essentially, what you do, you set that to your region. We provide a spreadsheet for you to assemble information about the population age distribution, because the mortality is very different for old people than young people. And we provide a spreadsheet for you to load your actual local daily data into. And when you've done that, there is a process to go through to get the model to behave in a way that matches the data you've got. Now, this is the UK data, and I said a moment ago that the current growth in deaths is happening much faster than the simulated result. It's worth mentioning that the simulated result is it is reasonably close to the result that Imperial College produced in their March 16th report that went to government, that got the government taking this whole thing seriously. So the actual progress of the disease is already much faster than that Imperial College analysis feared. Now, why is it much faster? Well, one of the things that the Imperial College team had to do was take the information Maurice mentioned a few moments ago about how long people remain ill before they either die or recover. And they picked up the information from the research in China that said how long that period is. And it turns out that on average, I think, correct me if I'm wrong, Maurice, but I think that the average time before death in their findings was something like 10 days, and the average time to recovery was something like 22 days, something of that kind. With that assumption, we do not match what we observe actually happening. We have somewhere down here, we have the option to make that period of being sick before you die or recover faster or slower. So I'm going to make it faster, and make it faster. We get a closer match. I think faster in our model means something like 4 days before you die and 10 days before you recover. So that's what you do with the model. I think, Maurice, unless you want to, do you want to say anything before we open the thing up to questions here?
Yes, just one thing about that technical point you just made. There's a feature in the software that allows you to create two types of delay functions. There's the one that Kim showed you, which is called delay, and it's like sending things through a pipe. Everything that comes into the pipe at the beginning goes in rank order, first in, first out, and that means that it holds the characteristics over the course of the delay of the people that went in at the beginning come out the delay time later, and then new people coming in have to wait until everybody's emptied the pipe until they can get out. That means that you can only select an integer value for the faster or slower. So that parameter has to be 1, 2, 3. There are other types of delays in the model which are called first order delays, which is simply everything in the stock leaves the stock indiscriminate of when it came in. So somebody arriving at the hospital could immediately die and leave, or could immediately recover and leave. Both formulations are useful in different ways and are used in different ways in this model.
Okay, so there we go. I would be very happy to open up the discussion for questions, and if the organisers are happy with this, if they can unmute everybody, but everybody mute themselves unless they want to say something, that would be,
sure, we can really do that, Kim. Now everybody can unmute themselves.
Okay, so everybody who's listening, don't wait to put your hand up or anything like that. Simply unmute yourself and say something.
Kim, this is Colin Elwood.
Colin. Hello.
Yeah, I think Colin, can you speak? We cannot listen to you very well, Colin. Yeah, there might be a problem. Well, there's a question from Ken Nicholson. have you been influenced by the work of Donella Meadows and the MIT Systems team?
Oh well, absolutely. This whole thing is because of them. Yeah, as that's saying about standing on the shoulders of giants, isn't there? Well, yeah, those are the giants on whose shoulders Maurice and I and everybody else in the field are standing. Yeah, definitely. That's where it came from. That's what we owe everything we know to. So yeah, for sure.
Okay, so now Colin posted the question. Can you summarize differences between your model and the Imperial model one?
Maurice, you're probably better able to answer that question than I am, because you replicated their model, didn't you?
Yes. So we went through a validation exercise to map the Imperial College epidemiological model into the stock and flow framework. And we were able to verify that the stock and flow framework that they describe reproduces their results. So that is something that we're able to share with you as well if you want to look at it. The difference between the stock and flow framework that is described in the Imperial's work is different from the one that Kim is presenting here in some important ways. And what we have had to do is estimate the parameters that are used in this COVID-19 model that you're looking at from the mapping that we did to validate the stock and flow framework for the Imperial's work. So there are some differences in methodology and parameters, but we can tie this model directly to the Imperial work where the conceptual formulation of the model is the same. Where we've had to deviate, we've had to make some assumptions, and we've tried to use independent sources for all of those assumptions where the information is available.
Any other questions?
So there's 57 people out there. Surely someone else has got questions they want to ask, or comments they want to make.
I have a question. Could we do a poll?
Sure, yeah.
How many people would be interested in localizing this for a city or a country or a local area like their neighborhood for themselves, so they can see a little better what's happening around them, or for their families that may be in other countries?
Okay, so just for the sake of being fast, I will just put the poll that I had created. So if you want to answer this question, just say yes. The question, it says, have you done the task? But if you're willing to do this, say yes.
While we're waiting for those answers to come in, let me just show you what it is you need to complete. You need to put in the population age distribution. This is 0 to 9-year-olds, 10 to 19-year-olds, up to 80-plus-year-olds for your region. And you need to complete this table with any information you've...
I don't think people can see the screen or screen on always taking place.
Okay. Right.
We get what you're doing.
I'm being told that people can't see the screen if the poll's running. Is that true?
Okay, sorry. I'll close the poll. Yeah. So,
No
yeah.
worries. No problem at all. So how many people are saying that they'd like to try this on an area?
Yeah, so now it's 67% of 45% voted. So
okay.
Yeah, it gives you only the percentage, but let's say
So
around
what,
25 people might be like
those said that they'd like to, yeah.
Like around 15, 16 people could be doing that.
Unfortunately, I can't see the chat. If anyone does want to,
can I ask a question? Yeah, hi, it's Rachel Freeman. I'm just interested in just watching the news and the interplay between you've got the delays in the system in terms of seeing what's likely to happen in the future and what is happening now, and then you've got delays in responses from government in terms of enacting policies. Although the response to the models actually has been quite impressive in terms of how quickly the government was shut down, but there are other delays in the system, like for example in getting the testing kits out there. Right. So I'm sort of working on something a bit similar in terms of the delays in policies on between scientific projections and governmental responses on climate change. So it's a bit similar, I think, in terms of there's a sort of 2 layers of delay.
Right, yeah. One of the test parameters you can put in the model when you've got it running is you can set this thing here, which is at what rate of new cases per day does the government impose social distancing, and it's expressed in cases per day per 1,000 population. So that means it's configurable for any population that you're looking at. So if I set that to 1, that says if you've got a population of 1 million, government imposes social distancing when 1,000 cases per day are confirmed. Right. This item below that says how many days do they continue that policy before relaxing it. So if I change that from 1 to 0.2, you can see that you still get very big numbers of people getting infected. That's why social distancing has to be so severe. If I cut that social distancing contact to 1%, then it slows it down a bit more. But we're really up against it with this thing.
Right.
So that, to answer your question specifically, yeah, that's how we're figuring out the delays here. Was the policy delays? What does it take to push the government to act?
Right. Okay.
Hey, we have some questions that have been posted on the chat. So Amduth Kusiel asked, will this model feed into policy?
Maurice, do you want to say a word or two about what we hope will happen here?
Yeah, we can only talk about what we hope will happen rather than what will happen. We hope that people like yourselves will take this and use it to inform yourselves about your local area, and then if you have a high degree of confidence of what you've done with the model, then you can explain it, which we hope we can provide enough information to do that. You'll speak to your councillors or your local MPs and ask them to have a look at what you've done, and that may influence them. At the moment, there is no direct connection between us and number 10 Downing Street. We've been busy building the model. We do have, we've started to reach out to healthcare officials in the NHS. We've made contact with the healthcare authorities in New York City. We are in the process of speaking to the government of Canada about this and the World Health Organization. It's anybody's guess how long it will be before they or have time even to look at this and decide whether it's useful, that's not something we can have control over. But if by getting feedback from yourselves about how useful this is and where you might struggle to use it, we can continue to improve it, and in due course, if it's easy enough and understandable enough, policymakers will hopefully use it.
We should also add that that we know that there are many other groups out there trying to do something very similar to this, and it's entirely possible that they've got something better or something different, or they've got better contacts with policymakers or whatever. It's entirely possible, and we wouldn't in any way want to discourage policymakers using anything that's as good or better than this, wherever it comes from. This is not time to be proprietorial about things.
Yeah, we're going to be publishing an article in Medium later today, we hope, with some case studies that are being worked on for Hong Kong, Crete, Lombardy, Athens, possibly Bucharest, New York City, and others. And we'll show what the results are for those areas. We'll try and explain how they were localized. And one of the caveats is that we're not trying to compete with anybody's methodology or insights. We're just trying to offer something that might be complementary and might help. So if you want to see results from various locations, they'll be available to have a look at in that article.
Jez Rosenberg here from Bristol University.
Hello.
Can you hear me?
Yes.
Yep.
I don't know if you're aware, you're talking about kind of doing some of the modelling work and supporting. There is a rapid assistance in modelling pandemics call out, so the government is actually looking for help at the moment to help the modellers. Is that something you're aware of? Have you do you have the links into that? Maybe Rachel Freeman, you might be able to facilitate that. Is it just a thought? And then I have a question afterwards.
Yeah, thanks for that one. The short answer is yes, we are aware, and we have submitted it, haven't we, Maurice?
Yes, we've notified them that we're doing this, and we've given them links to the model. So we don't know. We haven't heard back from them yet. We're waiting for them to respond and interact with us now.
Okay,
there was a question.
Good. Well, and the question was, from what I can see in how you're structuring the model, the sort of assumption is that the whole population is not homogeneous, because obviously you've got parameterizing as to who dies and sort of death rates and that kind of thing. But have you looked at sort of segmenting the policy in different ways, so that social distancing may apply to different age groups to different extents? Has anyone done a more sort of heterogeneous policy analysis?
Well, yeah, that's a very important question. Can I just start by saying what our immediate next steps are, and get to that? So the first thing is that we've got a very crude impact of hospital capacity in the model at the moment. Basically, you set whatever the hospital capacity is, and then any more people in the hospitals can cope with get sent home. We're going to improve that. The next thing we want to add is a section for test, trace, and isolate. Basically, what it'll do in the model itself is it will take people out of the infected stocks, and it will park them in an isolated stock until they recover. And we hope that will be a rather important feature to tell people about how much testing is necessary, and how much tracing is necessary.
This is inspired by what would happen in South Korea, where they did extensive testing very, very rapidly, and it's proven to be very effective.
From a personal point of view, I can't begin to think why on earth it's taken us so long to do the same thing. But now back to your specific question. Yeah, we definitely, in an ideal world, we definitely would segment the population in particular. Hello?
Your audio was disappearing again.
Am I unmuted again?
Yeah, sorry about that.
Okay, no worries. Yeah, we definitely, in an ideal world, we would want to segment it and take out possibly the elderly. Sweden, I think, is experimenting with, well, it's awful to say experimenting, but their view is that the best policy is actually to have very strict isolation for vulnerable parts of the population, but basically allow the rest of the population to go about pretty much their normal daily business and presumably get infected and get resistant. I assume that's the logic of that. In order to do that, what we would effectively do is have two separate pipelines for the vulnerable and the rest, and have cross infection rates going between those two.
Okay.
I believe
thanks
we're
for
out
that
of
answer.
time,
Yeah.
but I'm very happy to continue answering questions if everyone.
Yeah.
Like.
I think Sean wanted to just mention something. He wanted me to. Sean, are you there? Sean, yeah. Sean, can you unmute yourself? Yeah.
Yeah. Okay. So yeah, thanks ever so much, Kim, and also Maurice as well. I was a really welcome surprise that you were able to join in too. I just wanted to bring this session to a close now, so we can have a good lunch and then reconvene at 1:30. I'd like to put my thanks to Kim and Maurice. That was an excellent session, and also congratulate you on completely redoing what you were going to present. I think I got the email from you about 9:30 last night saying that you were thinking of changing your slides to something a lot more technical. So thanks for putting that extra effort in for today's session. So we're going to break for lunch now. While lunch is happening, we're going to have some slides just rolling, showing some of the posters that are going to be presented in more detail later on. I'd like to thank everyone who's joined us this morning for your attention, and we'll see you at 1:30 this afternoon. Thank you. Goodbye.
Okay, I will show the slide deck, but I will post some of the questions to the panelists if they're happy to answer them through the chat. Maybe they can do that.
Diego, I don't understand why I'm not seeing any of the questions on the chat myself.
Okay, I will send them to you just right now. Let me assign them to you. Can you see them now?
Nope.
No.
I'm seeing things that you post directly, but I'm not seeing anything else.
I sent to you the.
Oh, hold on. What's this?
You should see some questions appearing because I have assigned them.
Oh, God. I had no idea that was a completely separate thing on questions. I do apologise.
Not a problem, Kim. For most attendees, it's combined into one, but for slightly different setups, such as yourself and myself and Diego and Hisham, you see it slightly differently.
Yeah, but this is a feature of the system. I had no idea that questions was different from chat.
Yes. So okay. I sent you all the questions that were missing. Right. We can like well, as we can show the deck of posters, and you can continue answer the questions online.
Sure. I can let me do that. I'm going to do it verbally, if that's okay.
Yeah.
The question here is there any SD community level collaboration going on for the development, learning and use of these SIR models where interested people or groups can join in, particularly to help transdisciplinary approaches to the pandemic? I'm not aware of one, but various people with some knowledge of this kind of issue. I know there's email traffic going on between them. I think maybe a more formal, organised collaboration would be a good idea, but I don't know how to make that happen. I think it needs somebody maybe from the health policy interest group to kick that on. Bronwyn's asking, can we see the impact on young people? Well, we would like to segment the model by age group. What the age group input does in the model at the moment is it simply ratchets up or down the overall mortality rate. So if you've got an older age profile population, then you'll have a higher death rate. If you've got a younger profile, you'll have a lower death rate. It's not actually splitting out separately what happens to different people, unfortunately. It is possible to do, but it is heckish complicated. How does the complexity of this model compare with that of the Imperial Group? Maurice, are you still on the call?
Yes, I am.
Okay. So the question is, how does the complexity of this model compare with that of the Imperial Group? I'm guessing it's a little more complex, but not much.
I would say it's similar. You know, there are nuances that we've chosen to introduce so that we can ask the policy questions that you've put in, and in particular, we don't know the level of detail that Imperial have embedded in their model around the interactions between the hospital system, the healthcare system, including how many doctors and nurses are getting sick and being self-isolated. We built this simulation with the intention of migrating to something that would allow us to analyze that. And we published a sketch, a simplified version of that a little over a week ago. On the development path, and the reason this model is a little bit more complex, is perhaps slightly more detailed than the Imperial model seems to be, bearing in mind that we have not actually had a chance to speak to the Imperial team. We have reached out to them and asked them to spend some time with us, but that hasn't happened yet. Our model anticipates the interaction between the healthcare services and the progression of the disease, and that's the next step on our path.
So Colin's asking if we're planning to segment by different parts of the workforce, and that's beyond what we can do at the moment. Colin, we would love to be able to do that, but we're focusing at the moment on extending it to do a much better job on the health system itself and the impact of testing. Regional local models. I think I saw somebody, yeah, Sinead is asking if anybody is modelling Northern Ireland. Well, Sinead, just get the model and put the Northern Ireland numbers in it. That's all you need to do, and it shouldn't take much long.
Hi, Kim.
Hiya.
Hi. I'm actually doing that alongside the South of Ireland.
Okay.
I was just wondering, was anyone else doing it?
We wanted to do it.
Sorry, Maurice, after you.
I was saying we're looking for somebody to champion that.
Yeah.
Stephen Allett was going to try and find somebody if Sinead is interested in that. Please proceed and contact us for help if you need it.
Oh, that'd be perfect. Thank you so much.
Sinead, what is your?
Hello.
Sinead, what is your? I don't have your last name. I just know I can't see it on the chat.
Madden, M-A-D-D-E-N.
Okay.
The next question is, I guess one possible use of disaggregating the models geographically could be to plan resource use and sharing, e.g. I'm aware that in region cities that have lighter numbers, there can be higher availability of ventilators in one area to another. There could be use in rapid resource planning and transferring of patients' resources to save lives. That is a possibility. I don't think Maurice may have a view on this, but I'm not sure this model is going to tell people anything that they don't already know about that.
Sorry, I tuned out of the question. Could you just repeat it? I apologize.
Could this if we ran this model for more than one region or more than one city, could it be used in rapid resource planning and transferring of either moving patients to areas where resources are better, or moving resources to where from one area to where they're needed more? I think that's a much more operational and tactical thing, which is best handled by people just being in touch with each other between cities.
Yeah, there is an idea that we have been talking about within our group, but how to make it work is a technical challenge. Just imagine if it were possible to define a localization of the model as a hospital catchment area. There are about just over 1,200 hospitals in the UK, and if there was one of these models running for each hospital catchment area, then they would all be running simultaneously, and we would see forward a few weeks where resources were short of needs, and in that way we could have a contemporaneous picture of the entire UK hospital by hospital. So it is in principle possible. It would require more than 1,200 copies of the model and perhaps more than 1,200 volunteers to run each copy consistently, and to make sure that there were not inappropriate overlaps. So in theory, it's possible, but it's an idea rather than something we're attempting to implement right now. And what makes it possible is the open source distribution of the sheetless software that anybody at any time can open up any model and run it independently, and then we can collect the information and aggregate it and compare the performance of each model versus the others. So I would say it's possible. It's a valid idea, but we don't have the resources to implement it yet.
I think that's it, Maurice. So that's the end of the questions. So
okay,
I think we're done.
All right.
So I'm going to sign off, and we'll be in touch separately. Yeah.
Yeah.
And I'd just like to say thank you to Kim and to Maurice for that excellent presentation, and also answering all those additional questions. The slides are available, and I think your email addresses are included in the slide deck. So if anyone's got any questions they'd like to ask either of you, then do please. I'm sure Kim and Maurice would welcome contact. Okay, thank you both.
Absolutely, Sean. And Sean,
slightly chaotic morning, but hopefully we've got somewhere.
No, it's very good, thank you.
Just for me, thank you for letting me participate as a panelist today. That was not something that either of us had planned on. So I really appreciate the opportunity.
Everyone's in a very fast-moving situation at the moment, and appreciate you taking the time to spend it with us. Thanks.
Okay. All right. Well, enjoy your lunch, everyone, wherever you are.
And so we will reconvene at 1:30 for the kickoff of the afternoon session. Speak to you all soon. Thank you.